podcast for Chapter 8 of Field Methods in Hydrology on the topic of measuring water velocity. Rivers are very ordered systems, and if you think about it, they're ordered because you have gravity pulling this overabundance of water that's been organized into a channel or some other concentration. It's pulling it downhill. So gravity is the fundamental driver, and that coherent body of water is going to be moving in a systematic way that's largely predictable by the laws of mass momentum conservation. So we can take advantage of what we know about those fundamental laws of nature to help guide us in the design of how we measure it. And of course, there's a variety of technologies available. Now for me, I have a little bit of a love-hate relationship with velocity because it's so important to know, but on the other hand, people over-rely on it for things that it shouldn't be used for. And in terms of measurement, it's another one of these things that you feel like ought to be relatively easy to measure, but it's actually fairly difficult and very time-consuming to measure, so that can be frustrating. But it's very important because velocity governs sediment transport, which in turn plays a large role in scour and deposition to change channel forms. Organisms also use velocity as an indicator of where they're going to do their different functions at different life stages. So it plays an essential role in both the physical and biological aspects of a river, and therefore it's really something that we have to be able to measure. So what I want to do in this presentation is, as usual, cover some basic concepts in velocity and then introduce the technologies for measuring it. If you've had a course in fluid mechanics, some of the basic concepts I'm going to introduce should be repetitive, and of course hopefully you have had that, but if you haven't, then this may be your first introduction to these ideas, and so some of this information may seem new and a little bit challenging, but it's important information that you need to know. There are some basic constants, some numbers that we use, and I'm giving them to you here in metric units. I'm actually going to start at the bottom and just point out that velocity is often denoted using the symbols U or V, and of course V for velocity. But you have to remember, velocity, unlike depth, velocity is a vector, not a scalar, and so therefore it has both a direction and a magnitude, and often we'll break velocity up into different components, like the component going right down the river, the component going transverse to that, and then the component that's up and down. So with those three components, we might use U to represent what's going down the river, V to represent a cross-channel flux, and W to represent the vertical flux. Or other vector notation, it might be UI, UJ, UK, something like that. Okay, so some of the constants, obviously G, the gravitational constant. Water density is going to be very important, just the mass per unit volume of water. Specific weight, dynamic viscosity and kinematic viscosity, and these two show the ability of water or any flow as a medium to deform as it's imposed on by the force of gravity. And then the variable shear stress, which is a representation of the effects of friction at the riverbed water interface. And shear stress can also be given in units of velocity. If you take shear stress and divide it by the density of water, take the square root, it will give you units of velocity, so we call that shear velocity. So those are some basic numbers. Some of these are temperature sensitive, so you have to be mindful that depending on where you're working, you might have to look up alternative values. But these are fairly common numbers that we use. So the first aspect about flow in rivers, or really over any ground surface, is that it's flow that's occurring as boundary layer flow. So this is layer of fluid over a frictional surface where the velocity is impacted by shear stress induced by that surface. The only exception where you might not have this would be like atmospheric or oceanic flows where you're far, far away from the bottom. And in a fluid mechanics course, you'll learn where that boundary transition is. But from the sake of a river or hill slope perspective, if you have flow, you're going to have boundary layer flow. The next aspect is whether the flow is laminar or turbulent. Laminar means that the fluid particles are moving along pathways. They don't have to be straight lines, but they have to be pathways where those are not crossing. Turbulent means that there's a lot of crossing over, and that means that there's mixing that's irreversible. The transition between laminar and turbulent is defined by something called the Reynolds number. But before I go through this, I'm going to skip ahead to the next slide and show you two visualizations. The first one on the left, we'll start off with a laminar condition, and there's dye being injected on the left, and then it's moving across, and you'll see that the dye stays in that line. Then it will transition to a turbulent flow where you'll see that the water will begin to mix between the dye and no dye area. So you see, okay, here's the mixing. So it almost looked like nothing was happening under the laminar run. I'll do it one more time. Here it is. You can kind of see that there's some movement taking place, but it's essentially smooth. And here's the turbulent case. Now let me show you a little bit longer example of an experiment. You can find this on the internet. It actually is a real phenomenon. And wait, go back one here. I don't want to show the answer yet. But okay, watch this video. It demonstrates laminar flow conditions in a relatively high viscosity material.
Corn syrup dyed red.
Okay, so we just injected some red corn syrup into some clear corn syrup.
Now we're going to put in corn syrup dyed green.
Okay, so now we're injecting a second blob, and this is going to be a green blob.
Now we're putting in blue corn syrup.
Okay, here comes the blob of blue. Okay, now they hold
now we're going to rotate these.
And they slowly rotate.
Slowly. 5 times. Is this one?
So they're going to rotate it 5 full rotations. That was 1.
Notice the flow is laminar because the Reynolds number is less than 1. Is this 2? This would be 3. This is 3.
Okay, rotation's going.
4.
4.
5.
5 rotations.
Now we're going to go back.
Okay, well, we're taking this setup and now we're going backwards.
That's 1. Backwards 2. Backwards 3. Backwards 4. Oh, I see. One more. So we have a couple of coaches. Very good.
And there you have it. Okay, so I know some of you are experiencing psychological shock and awe as to how that actually took place, so you may want to watch that 1 or 2 more times. Here's an explanation that I pulled off the internet. When you have a very viscous and slow-moving flow, it's called creeping flow. And as a result of that, the viscous forces far outweigh the inertial forces. So it's basically moving in a way that is retraceable in the opposite direction. Okay, so the threshold for determining laminar or turbulent conditions in a river is going to be determined by the Reynolds number. Well, that's true anywhere, of course. And it's the velocity times the depth divided by the kinematic viscosity given by the symbol nu. If the Reynolds number is greater than 750 for an open channel flow, then it's turbulent. Now let's take a look at some calculations here that will help convince you that rivers are essentially almost always turbulent. Because the kinematic viscosity of fluid at a typical temperature in water, is 10 to the negative 6, If you want to end up with a number less than 750, then that means that the velocity times the depth is going to have to be less than 7.5 times 10 to the minus 4 meters squared per second. Oh, sorry for that comma that's in there. If the depth is 1 centimeter, which is 0.1 meters, then that means the velocity is going to have to be less than 7.5 centimeters per second, which is relatively slow, not impossibly so. On the other hand, what river is only 1 centimeter thick? That's not really a river. I mean, that's basically conditions that you would have over a ground surface. Like if you have overland flow, like saturation excess overland flow or Hartonian overland flow on a hill slope, it is possible in that kind of setting where you could have very thin flow and moving very slowly, and it might possibly be laminar. However, let's look at a river, because rivers aren't 1 centimeter deep. Let's say they're a foot deep, which is like 30 centimeters or so. Well, for depth of 30 centimeters, you'd have to have a velocity less than 2.5 millimeters per second, which is tiny. That's essentially being in a pool, or right along the bank where, in a very shallow, slow-moving, stagnant water, there is a chance of having laminar flow. But having that small location as laminar doesn't mean that the river as a whole is, and the river is best characterized as a turbulent boundary layer flow. The next thing I'd like to present is a couple of basic concepts about rivers when we start to look at open channel flows. And the first is a variable that we use to help characterize the cross-sectional shape of the river, and it comes into play when we do some of the mathematics to calculate things related to velocity. It derives from the basic fluid mechanics of open channel flow and pipe flow. So if you take a civil engineering fluid mechanics class, you'll see where this comes from. The important thing to understand for this class is that hydraulic radius is a parameter or variable representing the cross-sectional shape. So we define the hydraulic radius as cross-sectional area divided by wetted perimeter. On the left we have an image that's kind of like a natural channel. We've got the bed of the river, and then you can imagine that there's water inside of that. What you can see here is the river is going in and out of the page, and this is like a slice through that, and you're looking at that cross-section. The cross-sectional area is the domain, in this box I'm drawing here where the water is basically. And then the wetted perimeter is the line at the interface between the bed and the water from one bank to the other. So we can draw that here as the wetted perimeter. Now, if you have a true rectangular channel and you have a left wall that's wet and a right wall that's wet, then it's not just the bed. So it's not necessarily the same as the top width of the river, but it's the left, bottom, and right walls all together making that wetted perimeter. So it's a little bit different from what you see in this presentation, that image. Let's just think about what this might mean for the simple rectangular channel. Imagine a case where a river is 100 units wide and 1 unit deep, whether those units are feet or meters, whatever. And so you could, if we put it into this equation, we'd get 100 times 1, which is 100, and on the bottom we have 100 plus 2, which is 102. Well, 100 over 102 is a tiny bit smaller than 1, but not significantly smaller. So basically what happens is this 2D, it adds a very insignificant component when a river is very wide relative to its depth, and as a result, we can eliminate 2D, it simplifies here, and we can eliminate width, and then the hydraulic radius is revealed for very wide, shallow flows to be D. And it also means that as flows get deeper and narrower, we're going to deviate from D, but it's going to be less than D. Okay, so that's the hydraulic radius. Another concept I'd like to introduce to you is the idea of a velocity profile. Profile just means how does something change in a direction, just like as you're moving along a transect or a cross-section. But the profile could be a transect down the river, across the river, or up through the water column. So for example, here I've just drawn a simple Cartesian graph But now the x-axis is velocity and the y-axis is z. Because if you want to show a vertical profile, then you'd want to know how does you have to put it on x. So it's not z as a function of x, it's v. It's not z as a function of velocity, right? Because z is the given. It's an independent variable. But of course, we're changing in the vertical, so we use z to denote that. The question I have for you is, what is the shape of this profile? So just to illustrate this, here is a river, and I've driven it as a parallelogram just to reflect the fact that the river is sloped. So if we go from upstream to downstream, and then we're going up in this direction in the vertical, staying perpendicular to bed, would be a measure of depth. And then here I've drawn a variety of possibilities. It's possible that it's slowest at the top, because this would be the lowest along this axis, and it gets highest at the bed. It could be nonlinear or linear. It could be uniform through depth. It could increase in depth, or it could decrease with depth. And then if it's increasing, for example, it could be a linear increase, or it could be a strongly nonlinear increase. So of these choices, just pause for a second and think about which one you think it is. And when you're doing that, remember, this is an example of how the river is organized. So what would be the processes causing velocities to be higher or lower in the water column of a river? And this is a good example to illustrate that when we're making measurements, we have to be mindful of that natural organization. And in fact, because there's friction along the bed, we have a gravitational flow. The gravity is pulling water down, and as it rolls as it moves along the surface and interacts with it, it gets sheared dramatically, which of course creates the turbulent flow that's there because it's not highly viscous. And so as a result, you tend to have a nonlinear profile. It's just not exactly as shown here. I'll show you some in a moment. But basically really low along the bottom and then rapidly increasing and reaching a near constant. At the surface, unless you have ice present, the surface is experiencing very little friction between the air and the water, and so it tends to reach its maximum velocity farthest away from the bed. We can also ask the same question about the horizontal. So now that you've heard the explanation for vertical, which of these profiles would be representative? And so what I'm showing here is like the flow is going from here to here. So this would be a profile where maybe you have a V-shaped profile where it's slowest in the middle and linearly increasing to the edge. Maybe it's more of a parabolic profile, slowest in the middle and fastest at the edge. Maybe it's a uniform profile, and then maybe it's the inverse. Maybe it's increasing towards the middle, linearly or non-linearly. So pause for a second and think about which of those you think it is and why. Okay, so the answer is, just as we have the most friction along the bed in the vertical case, we have the most friction along the bank in the horizontal case. And so as a result of that, we get a nonlinear parabolic function. And if you take these two and put it together, you would imagine that the fastest velocities are taking place at the surface in the middle of a channel. Here's some data to illustrate vertical velocity profiles. What you see here on the x-axis is velocity, and then on the y-axis this is depth. So zero depth is at the surface and depth is increasing here in units of millimeters and millimeters per second. So these are depths, up to 1.7 meters or 2.2 meters of water depth, so relatively shallow flows. And every little dot here is a measurement that's made of the velocity in a river in New Zealand. And when you put them all together, then a best fit line is shown as this white line through the middle. And you can see that they can be quite different. They're generally taking on a nonlinear shape, although here it's very flat, but it has apparent linear range, but that's all nonlinear functions have a short range where they appear linear. But the functions are dramatically different from profile to profile, which is a result of the fact that over a complex riverbed, if you're gravel, cobble, or boulder, all kinds of things are happening. If you're a very fine-grained riverbed, or just you're a smooth riverbed, then you would see a more ideal profile. And here is the traditional profile equation that we use. Now, why am I showing you this equation? It's going to be very important in a lot of the ways in which you use velocity in your career. If you ever want to do anything about figuring out how channels change or where sediment is moving or how much sediment is moving around, this profile equation is a very powerful tool that you can use. I use it a lot in my career. So that's why I'm presenting it to you. And it's good to be exposed to it at least once, even if you don't end up using it. What you can see is there is a canopy, so to speak, of the grains on the bed that are poking up out of the bed. We have to define an area that we call the virtual bed here, which is above most of that mess. And relative to that location that's above the bed, then we can start to have a profile. And the profile has a logarithmic function equation, so we call the log velocity profile. And this is the equation. If you look at the interior of the log function, you'll see that it has a ratio of z over ks. What we're doing here, we're taking the elevation above the bed and we're scaling it relative to the particle size or roughness of the bed. So what this is saying is the velocity is a function of how high we are above the bed relative to that roughness. Are we twice as far up from the bed as it is rough? Are we 10 times? So basically like that. The fact that there's a constant in here isn't important for what we need to do in this class. So we have this ratio. Ks, this roughness parameter, is basically a function of the grain size that's on the bed. Sometimes it's a fraction, sometimes it's a multiple. It just depends what that is. If you have a concrete bed or plastic or glass or something like that, there are often textbook values to use, but otherwise you can look in the literature and get an appropriate Ks value based on the substrate that you have on your riverbed. So this is the profile equation, and you can see it gives us the velocity, this is the downstream-oriented velocity at any position z above the bed, and it's a function of that ratio I was talking about. And you can see it also is a function of the shear velocity. Now this is a tricky part, of course, because how would you calculate that shear velocity? So in fact, the way we often use this equation is not to calculate the velocity, but to calculate shear velocity or shear stress that's inside that term. So if you measure the velocity at a point above the bed, and you estimate the roughness, and you measure, of course, the elevation where you took your velocity measurement, you can back calculate the shear velocity and shear stress. There's also a depth averaged equation if you take the integral of the profile equation. And so here U bar is depth average velocity, not just the velocity at one position above the bed. And now it just changes so that we have a different constant, and we now have hydraulic radius. And usually this depth average equation is applied to an entire cross section, but there are other people who will take this depth average equation, substitute water depth, and use this at any point in the river. So on our field trip where we go to a river and measure a whole bunch of stuff, the velocity, you'll have the opportunity to measure these different cross-sectional, vertical, longitudinal profiles of a velocity in a river, as well as to apply this equation to calculate the shear stress in the river. Another important thing that's going to come up later in the next chapter when we get to discharge is that we often would like to simplify the measurement of the depth average velocity. And this is one of the places where my love-hate relationship comes in. It's like we need to know the depth average velocity, but are you going to sit here and measure the profile at every single location in a river? Like if you're doing a discharge measurement, as you'll learn next time, you're going to need 30 measurements of velocity across the channel. If you also have to put in 10 to 30 measurements in the vertical, it basically becomes unfeasible in terms of the time it would take. So the simplest approach is to find the one place in the profile where you exactly match the mean velocity in the vertical. And that turns out mathematically to be a place that's 0.6 down from the surface in terms of the total depth. So if I measure the total depth and I go down 60% of that from the surface, then you get to this location, which is also going up 0.4 up. Okay, and you'll see that we're going to have a sensor technology called a top setting weighting rod that I'll show about in the part 2 of this presentation that shows how you get to that location. So you don't have to do all this math in the field. But in any case, you get to this location, and if you were to make the measurement right there under ideal conditions, it should equal that depth average velocity. However, in real field conditions, it can be variable, and especially as you get to deeper flows, you'd like to have more measurements. So the alternative is to measure at 80% of depth towards the surface and 80% of depth towards the bottom, so the 0.2 up and 0.8 up positions. If you measure just those two and skip the middle one, you'll get a significantly improved estimate. If you measure all three, you'll get your most accurate measurement apart from doing an entire profile. And here's some examples of some vertical velocity profiles that we made on the Mokelumne River here in California. And what I've done here is fit equations that show those profiles. So in this case, I'm allowing it to solve for both the roughness and the shear velocity that gives the optimal value. And I've done this for 3 different size classes, I believe from finer to coarser, but I haven't done this in a long time. And then just the mix of all the sizes together. And again, you can see a lot of different shapes to these profiles. Of course, when it's really shallow, it's hard to make a lot of measurements compared to when you have deeper flow. And the shear velocities and roughnesses are all quite different, so it can be fairly confounding. And then the last thing I just want to show you conceptually is that if you were to measure the velocity at the surface, it is higher than the mean velocity. If I take that Mokelumne River data I was showing you and do a best fit line, what you'll find is that the average velocity is, with the best fit line, 0.71 times the surface velocity. So it's smaller than that by about 30%, 29%. However, depending on if you calculate just the direct deviation or error percent, you get a different number than this compared to doing a least squares regression. And of course, if you go into different shaped rivers with different roughness of the bed relative to water depth, what we call relative roughness, then you're going to get very different values. It could be as low as 0.6 for like a bouldery, cobble, very shallow river, up to a value of 0.9 for a very deep and smooth river. So it makes it very hard to use surface velocity, but I will show you a method for measuring surface velocity as part of the Part 2 podcast. Okay, so that's it for Part 1, and we'll move on to Part 2 momentarily.